Everybody, we're starting from the point where we ended last week, and it is the first law of thermodynamics. We stated the following thing. D is there was two contributions. The first contribution is, well, the heat that we can pump in or pump out into the system or out of the system. Okay. Another contribution was the energy or the work that we performed on the system. Okay, there are several ways of how to define the work, and we define the work as the work that was performed on the system and not the work that was performed by the system. Okay. All right. We already treated the heat transfer into the system and why it actually contributes to the energy. And now I would like to go and discuss a little bit what is, so this is work and this is heat. And I would like now, right now discuss what is work and how we define it. So for us, work, it is the generalized forces that we have inside our system multiplied by modifications of the general variables. So those are generalized forces. And those are generalized variables. The idea behind this expression is, if you remember, if you have a constant force, work was always F dot dx. Okay. So you've been taught this in regular mechanics. And this is the same idea that works over here. But we have generalized forces and generalized variables. Notice this is a dot, so it's a vector multiplication. So what I mean by F dot dx is F1 dx1 plus F2 dx2 plus F3 dx3, etc., etc., etc. Now, why I call those generalized forces and I call them general variables? So first of all, let's look at an example. Let's assume that I have a pressure, I have a volume of a gas, okay, and I'm trying to squeeze the gas or let the gas expand. So what is the work performed on the system for such an example? Okay. Gas. So we know that we need to write it down in some sense, in some form of generalized force and general variable. So the variable that is modified during the expansion of the gas or squeezing of the gas, it's the volume, right? So dx1 is going to be dv. This is our generalized variable. It's not position, it's not position in axis y, x is just the general volume of the gas. What is going to be the force? The force is going to be pressure. And it's not just the pressure, it's the external pressure that I extend on the gas. Great. Am I missing something over here in this formula? So this is the work done by somebody who is pushing and squeezing the gas, right? Not exactly. Do you remember what I said? What is this? This is the work that was performed on the system. So if I'm having an external pressure, I'm trying to squeeze the gas, and my P external is positive, when I'm trying to squeeze the gas and I perform work on the system, the volume of the system decreased, right? So if the volume of the system decreased, all of this is negative. But I increased the energy of the system, I squeezed it. Okay, so the work is has to be positive. This is why, in this specific example, I have to add a minus over here. So my generalized force for this example of pressure and volume, the generalized force is minus the external pressure for the gas. This is the generalized force. And PdV and dV, this is my generalized variable. Let's do something similar with if I have a string. Okay, let's assume that I have some elastic string, and I'm trying to perform a work, okay, by doing something external on the system. Or elastic element, let's call it elastic element in general. Now, what I have in my elastic element, so first of all, I have tension. Let's assume that it's a one-dimensional elastic element, so I have a tension. Let's call it tau. This is my tension. And the work is done when I extend my elastic element, right? So here I would have dl. Do I need a plus or minus sign over here? Do I need a minus sign? Let's ask it this way. Do I need a minus sign? I need a minus sign here. And I'm claiming that I actually don't need a minus sign. I need a plus sign for this situation. Why again the plus sign? Because when I perform the work, I applied this tension, I extended the length of my elastic element. The total work, or this expression here, is positive. And I actually performed some positive work on the system. dl is positive, tau is positive, so I don't need to assign a minus like I did in the gas. I can think about other magnetic forces, electric forces, etc., etc., etc. It's always going to be, you have a generalized variable and you have a generalized force. Now notice something from those two examples. The generalized variable is extensive. What I mean, I increase the size of my system, my volume is increased proportionally to how much I increase the size of the system. So dV, or V, is extensive. When I increase the size of the system, L also increased, it's also extensive. But nothing really happens to my pressure or the tension. So generalized variables, they are extensive. Since energy has to be extensive, right? Work also has to be extensive. This means that my generalized forces are intensive. This is a general rule. When I write down work in this form, the generalized forces are always intensive. The generalized variables are always extensive. In total, extensive multiplied by intensive is going to be an extensive quantity. I need an extensive quantity since I assumed, remember last week, I assumed that everything that we're going to do is concerned with energies that are extensive, right? So this is why I need extensive multiplied by intensive variable. Okay, so forces, generalized forces, intensive, pressure, tension, etc., etc. Just a second. And the generalized variables that describe the system are going to be extensive. Yes?
I remember last week you
intensive, it's a quantity that's independent of the system size. If I take two systems, right? If I take two systems and I bring them together, the size of the system is multiplied by 2. But the pressure, if the systems are exactly identical to each other, the pressure is going to be the same. So intensive is independent of the system size. I'm increasing the system size and those guys stays exactly the same. Great. So in those two terms, work is actually easier to control, right? We can impose something like we can modify the intensive forces, generalized forces, or we can modify the generalized variables, right? Geometrically, for example. And this is how we can control work. So by controlling work, we can modify the energy. What exactly do we do with the heat? So we also have to have some sort of control for the heat. Now, we can do, if in our example from last week, we can increase the amount of the burning material. This is how we can produce more heat flow into the system. But in general, in our class, we can impose some boundary conditions. So if I have a system and there's a bunch of molecules inside, when I'm saying that I have some sort of a control over the system, I usually mean either I let the heat flow in or flow out, or I impose adiabatic boundary conditions when no heat can either get into the system or get out of the system. So adiabatic boundary conditions, simply conditions, no heat exchange. Okay. So this is how we can control heat that flows in or flows out. Basically, we look on systems that we shut down the heat flow, or we let the heat get in and get out. Two basics and general conditions. Great. Now, so this is the control. Work controls by forces and by variables. Heat control by imposing the adiabatic conditions. But great, so there is something that we can look on in our equation, dE equals to dQ plus dW. So by the way, I'm putting a small line over here to simply say that it's not a differential. Okay? It's not a differential. It's some amount of heat. By the way, by using this adiabatic or in just relieving the adiabatic conditions. Heat is not a quantity that I can say, well, there is a small amount and it's like mathematical differential. Work, I can think about it as some function. Heat, not exactly. Okay, so we're going to deal in all of our class, from this point till the end of the semester, we're going to deal with equilibrium states. Okay. So the work that we've done on the system, the heat that we put inside the system, or the heat that we let get out of the system, eventually we want to do the following thing. We want to start from some state A, equilibrium state A, and we want to get into some equilibrium state B. So all the transitions of the system and the exploration, what can happen to the system, is exploration of equilibrium states. We can start from A, equilibrium state, can transition into some B, and B is also going to be equilibrium state. Now, what is this equilibrium state? So, broadly defined, is a state that it's independent of time. So, what is the equilibrium state? The first condition is independence of time. Yeah.
Are we talking about statistical equilibrium or thermal?
Great. Great question. So what do I mean by independence of time? So let's assume that I have a magnet. And this magnet, or a bunch of metal. This is a metal. And inside those metals, there are atoms and there are electrons. And they're doing whatever they are doing. I'm summing up all the spin of all the different atoms inside my system. And this is the magnetization, right? You've been taught this in maybe electrodynamics or more introduction to modern physics. The magnetization is the sum of all the different spins that I have inside the system. Great. So what I assume, so M is this my magnetization. But each spin, because it's affected by random noise, because it's affected by some interactions with other spins, it's not constant in time. Right? The spin can be in this direction. From time to time it can change to another state and be in that direction. And then it can be in the other direction. So as a function of time, each spin is actually not stable. Each spin is depends, or its position actually varies as a function of time. Now in statistical physics or in thermodynamics, I don't have this perspective of one single spin. I'm looking on the total magnetization as a function of time. And what I see that due to this random fluctuations of different spins, what I will observe that the magnetization is actually fluctuating. Right? It's always like that. Why? Because there are huge number of constituents. Remember, the Avogadro number is very, very, very large. It's not one. You cannot assume that Avogadro number is 1. So sometimes physicists assume that numbers are 0 or 1. You cannot assume that Avogadro number is 1. Never. There's a lot of fluctuations. When I'm saying what is equilibrium independence of time, I'm saying when I average. There's always fluctuations. If you've been in the lab, you perform a measurement, and then you perform a measurement again, there's always some differences. When I average, I see that the average value does not depend on time. Okay? The average value is always constant. Okay? So I could maybe obtain some result when the average value itself will do something like that, right? This is not an equilibrium state because it depends on time. But on average, over all the different spins, and the average value is constant, then I can say, well, it's independent of time. So statistically, this is the right answer. So independence of time. By the way, sometimes it's really fragile. What depends on time and what is independent of time. So if we look on this guy, or if we look on the windows, they look stable to us, right? And they look that nothing happens, and they're indeed independent of time, but some materials, like glasses, they actually depend on time. They're not in equilibrium. Glassy materials are, well, it takes them enormous amount of time to reach equilibrium. By some, we're talking about billions of years, right? So those materials are out of equilibrium, although they seem to us as if they are. So for us, we will assume that an equilibrium state is some state where we don't have any dependence of time of statistical quantities. our energy is an average. Why again? Because all the different molecules doing something, so the energy, the total energy, always fluctuates. The average energy never does in equilibrium. 2, the states depends on small number of variables. What do I mean by small number of variables? So I described to you those generalized variables, right? For example, it was the volume of the system, it was the length of the system, it can be the number of particles inside of the system. All of those, all of those define specifically the equilibrium state. Why I say small? Well, we are going to describe them using like 5, 6, 7 variables. It's small compared to the Avogadro number of particles, right? So the amount of degrees of freedom is enormous, but I forget about all those degrees of freedom. I say the only thing that I care are my intensive forces and extensive generalized variables, and only those somehow define my equilibrium state. Number 3, and actually an outcome of number 1 is we don't care how the state was reached. So if I'm looking on a box with a lot of molecules inside, you can say, well, previously I shaken the box, or previously I did something else with the box, but after I waited a while, this while can take a long time, but I waited a while, I'm looking now in the box, I'm saying, oh, it's in equilibrium. I don't care if I shaken it previously or what I have done to it previously, because the state only depends on those specific number of small variables, and if those are set, it's like a function. Think about it as a function. If I setting the variables of a function, I don't care about what I have done with the function before. That's it. So this is number 3. Great. So here we are stopped talking about the first law of thermodynamics. Yes?
Why should you say glass was in equilibrium if it seems to be stable and we don't care?
Because as you look on it microscopically, you will see microscopical flaws inside the system. And there are experiments that they actually heat it a little bit above the home temperature. So you have a piece of glass and you look on it. Not those glasses, their time scale is extremely long. But you can take a glass that looks to you rigid and it will start to form small droplets, and those droplets will disconnect and fall down. Okay? So glass, there is a constant flow inside the material itself. It's a very interesting material. Very, very interesting material. It's because of this long time scale that it reaches equilibrium. Any other questions? Yes.
So, translating those axioms to mathematical terms, we can say that axiom 2 means that the system is non-chaotic, and axiom 1 means...
No, it's not about chaos. It's not about chaos. Chaos, it's something completely different. Chaos is dependence on initial conditions, and it usually happens in open systems. So the system can be chaotic for short times, but eventually it will stop being chaotic. It's about something that is called ergodicity. But
yeah,
don't mind about
That's what
it.
I wanted to ask. The first axiom means that the system is ergodic, right?
We don't need to use those terms now, but you're right.
Oh, okay.
Any other questions? Great. So we're going to law number 2, and it is the second law of thermodynamics. The second law of thermodynamics. And the second law of thermodynamics has to do something of, well, great, Stas. You described there is an equilibrium state. You have those three procedures or general claims, but how practically you're going to find this specific equilibrium state? I will give you a system, okay? I will give you a system, and please tell me what is equilibrium. The simplest example is I have a box with a bunch of molecules. Some of them are red and some of them are blue. And I put a membrane, so this is a two-dimensional box. The size of the box is fixed. And I put a membrane inside this box. And the distance of this membrane from the left-hand side is x. Okay. Now, what happens? So, all those molecules are doing something. They never sit, right? They jiggle around. They bombard the membrane. The membrane is, it's important, the membrane is free to move to the left and to the right, okay? They bombard the membrane. They bombard the exterior of the box. They sometimes, because their size is not zero, they sometimes hit each other, right? So something happens. And I ask, well, how do I find an equilibrium? Well, I have two ways. The first way is weight, right? Independence of time. After a while, well, this membrane will move to the left, it will move to the right, and after a while, I will find some general position of this membrane, x hat, okay? And this position will describe to me an equilibrium state of the system. Great, okay, so I can always give me a system, I will wait a while, and after a while, it settles due to these conditions over here. If it's not, well, I will say just haven't reached equilibrium yet. And so, well, this is equilibrium. And I want to compute, right? Eventually, I want to make predictions. Physics is not only about going and measuring stuff. Physics is also, or any science, is making falsible predictions. So I can go and check whether this happens or not. It increases my understanding of the nature around me, and it also contributes to the science. Or if I understand something, maybe I can do something else to explore whatever is happening inside the system. So the question is, how do I know where this membrane is going to settle? What is x hat? So what is the principle that allows me to calculate where and how equilibrium will occur? This is the second law of thermodynamics. And as in the first law, we start from some axiom, because conservation of energy is an axiom. Well, it always happens, as far as we can, we have looked in our world. So the same happens for the second axiom, and it's the following. So first of all, we have to define something which we call entropy. Entropy. A monotonic, non-monotonic growing function of energy. Okay. So in general, I say, well, S is my entropy. It depends on the energy and maybe some other variables, extensive variables of the system. I would say that it depends on the energy. So as energy grows, so the entropy grows. And I also would say that it is extensive quantity. Okay. It's extensive quantity. And how I define or how I do something about finding equilibrium. So the second law basically says the following. If I start from equilibrium state A, and I reach equilibrium state B adiabatically, then I say the following. SB is greater or equals to SA. This is the minimal. There are several definitions of what exactly is the second law of thermodynamics. We will use this minimal definition of the second law. By the way, what happens if from B I can go adiabatically to A? What will happen then? According to the second law, SA grows to greater than SB. And in this case, where the process, I can go from A to B, or I can go from B to A reversibly, okay, by changing little by little all the different variables inside my system, but not letting the heat in or not letting the heat out. For such a process, if they are connected to each other, I would say that SA equals to SB. Reversibility. Great. So this is the statement. How it allows for us to find the definition of an equilibrium state. What can I do in order to find it? So let's play a little bit with transitions from state A to state B and adiabatical transitions. Now remember, and it's a very important point that we're going to use. The moment that I reached an equilibrium state, I don't care how I reached it. I completely don't care about the process. This is the definition. My function, it's only defined by the variables at this specific state, and it's not defined, the state is not defined how it was reached. Okay. So I want to see what I can get from this definition of entropy, okay, and how it allows to me to go from one state to each other, and most importantly, how it allows me to define what an equilibrium state is. Do I have a general principle that I would say, apply this principle, and this principle gives you if the state is equilibrium and what happens in equilibrium and what are the different variables and their values at an equilibrium. Okay. So we start from our function of entropy. And since I assume that it's a monotonic and growing function of S, I can say let's write down the differential, it's a function, the differential of this function. So what is ds for our case? So ds, we have two variables. So this is ds to de, right? And I keep all the other generalized variable constants. Here I will have de plus ds to dx of e dot dx. Now, when I say ds to dx, this basically means that this is ds to dx. It is ds to dx1, ds to dx2, and ds to dx. And if I have n variables that define my equilibrium state. Okay, so this is a vector, and here I have a dot multiplications between two vectors. Okay, what else do I have? So this is a simple, very, very, very simple differential. Some sort of additional differential I have, but it's not exactly differential. It's dE. Remember, so what is dE? dE is dQ plus dW. Or it is dQ plus f dot dx. Okay. Now, this part is nice. This dq, it's not really nice. Why it's not really nice? Because it's not a differential. It's just an addition of heat that was brought to the system or was pumped out of the system when I observe this change in energy. But what happens for reversible processes, for adiabatic processes? Right? So for adiabatic processes, I know adiabatic. I know that dq equals to what? Equals to 0. Okay. The moment that I say that dq equals to 0, I can say, well, this is a differential, then this is also a differential. When this is a differential, I can plug inside this form over here. Thermodynamics, as you've been taught in the class on thermodynamics, is just a lot of assumptions about functions of many variables. That's it. So whatever you're doing with thermodynamics, you assume something, you have a bunch of axioms, we have seen 2, and then you have what is called calculus 2 or calculus 3, basically calculus of many variables. That's it. Now, so what happens when we plug inside dE f dx? So we have ds, it equals to ds to dE with a constant x. Inside of dE, what we have, f dot dx plus ds to dx with a constant e, and we have a dx over here. So we assumed adiabatic. We also assume reversible. What reversibility means? I've cleaned it, but it was written over here. Reversibility means that when I go from one state to another state, the entropy is exactly the same. So for reversible processes, ds equals to 0. Simply 0. So I have 0 equals to ds to dE x f dot dx plus ds to dx e dx. Very, very nice. We can there is also a dot multiplication over here. Got it? So we can take dx out of the parentheses. So we have dx over here, we have equals to 0 over here, and inside we have ds to dE with a constant x plus d multiplied by f plus ds to dx vector e. And all of this dot dx. And I will write down, because dx is arbitrary, right? I haven't told you by how much I move the volume of the system, the tension, or whatever. So dx is absolutely arbitrary. That means that whatever stands in those parentheses equals to 0. So ds to dE x f plus ds to dx e equals to 0. You can say, well, Stas, it's very nice, very, very, very nice derivation, but you had 2 extremely strong assumptions. You used adiabacity, and most importantly, you use reversible processes. It's great, you start from process A, you reach process B in a very, very controlled form. Okay? And for this specific controlled form, you obtain this nice equation, but it's probably not applicable because there's a lot of assumptions about how you go from point A to point B. And I will say to you, well, no, it's not. Why it's not? It's not because this equation connects equilibrium. I started from equilibrium point A, I reached equilibrium point B, somehow by doing a lot of assumptions, but eventually, whatever happens at point A and whatever happens at point B is independent of the past, right? Remember, those are equilibrium states. This is the strongest assumption. The moment that I have this, that they are equilibrium, it's like, well, as long as I connect equilibrium point A and equilibrium point B, this will always hold. It doesn't matter how I go from A to B. This equation is very general. I can forget about reversibility, I can forget about adiabasity, whatever. Those are connections between equilibrium states. The states do not care about how you reach them. Therefore, this equation is very, very general. The problem is, I don't really know what is ds dE, what is ds dx, and I actually don't really know what's entropies, right? I told you, it's a function and it's a growing function. I don't really have an understanding or a feeling, as you would say, what's an entropy. The problem is that we won't have a feeling about entropy till the second half of the semester, but for now, bear with me that there is something like that that's entropy, and there is a general connection. But we can make this form somewhat nicer. What do I mean by nicer? Well, remember what we said about entropy. Entropy is a monotonic growing function of energy. Okay. So ds to dE, okay, it's greater than 0. Let's say greater than equal, okay? But actually, I can say, well, it is 1 over dE to ds. Okay? Do E to ds. And I want to introduce a new quantity. dE to ds, I will call it temperature T. You say, no, Stas, the temperature is whatever when I'm sick and I'm putting the thermometer in my mouth and it gives me a specific number, 37, that's temperature. I would say, well, who told you that? Temperature is a measure of something, and this something is actually the measure of how the energy is growing with entropy. I don't really know what entropy is, but I would say, well, whatever entropy is, how the energy growing with entropy, and the entropy is the amount of the disorder, we'll talk about this later. But how the energy grows with the entropy is my temperature. So ds to dt, ds to dE is 1 over temperature. Okay. Now, since this guy is greater than 0, my temperature is also greater than 0. Great. More importantly, I can substitute it over here, right? So what I obtain? I obtain that 1 over T F plus ds to dx E equals to 0. Okay, so basically ds to dx vector E equals to minus 1 over T F. Okay. Since this is general, this is also general for equilibrium states, and I can plug it in my general equation for the entropy. I have ds equals to ds to dE of x dE plus ds to dx E dot dx. Right? So what we have? ds stays ds. ds to dE, it is 1 over t. 1 over t dE. plus, what is ds to dx? Is minus 1 over t f. Minus 1 over t f dot dx. I multiply everything by t, and I transfer this part to the left-hand side, and I obtain that d equals to t ds plus f dot dx. So you remember that there was some sort of a dq over here? There is no dq now. This is a general equation that connects equilibrium states. In general, when I go from one point to another, there is an addition of heat that I don't really know what it is because it's not a differential. But now, when I assume that I'm going from one equilibrium state to another equilibrium state, I can express this heat in terms of entropy. I still don't know what entropy is, or I know what it is, but I don't have absolutely no feeling what exactly this, because, well, it's not velocity, it's not position, it's something different. But I have a general expression for how the energy changes when I'm going from one state to another. I haven't still explained to you what happens or how I define an equilibrium state, but we will do it tomorrow. Thank you very much. שבוע שעבר. יש טקס שבוע הבא? או שהיום?
כן, לא היום.
לא, היום יש טקס רבין, אבל זה מ-11. לא יודע.